Everybody, my name's Alex Carney. I'm a second-year PhD student at Dartmouth, and I'm a student in the FITS lab. I'm really excited to be here and present to you all, and in collaboration with Dartmouth Engineering, DARPA, and the NSF, I'm presenting non-reciprocal exceptional points in Magnon Photon systems. This is going to be our theory, our experiment, and our outlook. So our story starts with quantum magnetometry, essentially how you can use quantum effects to find and create superior magnetometers. And for the longest time, a really good way to do this was with paramagnetic defects, such as NV centers and diamond. However, recently, there have been advances in using ferrimagnetic resonances, such as yttrium iron garnet, or YIG, to do the same thing. And the major benefit with yttrium iron garnet is that you can get much higher spin densities without having the T2 dephasing errors that plague NVs once you push their spin densities to really high limits. Furthermore, you can realize this with a much simpler experimental setup. So you only need a bias field, a bias magnetic field, to initialize your YIG quantum state. You don't need any lasers or other complicated optical setups. And even with all of this, you can still get really high sensitivity, and in some cases even higher sensitivity, down to the picotesla range using YIG. So we're going to combine this with a promising new field in non-Hermitian physics called exceptional point sensing. And the relative basic premise here is relatively simple. Near an exceptional point, the spectral splitting of the system follows a square root response. And what this means is that theoretically, at that exceptional point, you could have infinite sensitivity to a perturbation parameter. However, there's a problem. I redid those simulations, and I changed one parameter out of the 6 by giving it a 3% experimental uncertainty rate. And what happened? Well, we see that our exceptional point sensor is no longer super exceptional. The square root response near the exceptional point is severely diminished, and the fundamental reason for this is because near the exceptional point, if you have any uncertainty, those two peaks as they split can no longer be distinguished from each other. We can even see this in experimental realizations of this work, where we see that near the exceptional point, where the sensitivity is supposed to be the highest in the entire parameter regime, we see that this square root is diminished, and we can't distinguish these peaks from each other. And in fact, this problem, which is called hypersensitivity, has become so prolific that the scientific community is divided on whether or not exceptional points enhance or aren't useful for sensing. So here's our contribution. We built a tunable platform to universally realize two-dimensional exceptional points. It's an experimental platform, and we conclude that frequency splitting readout is likely infeasible, but we propose a different method for using exceptional points called amplitude sensing with homodyne frequency measurement. Okay, so with that, let's go into our architecture. So we're going to need some harmonic oscillators to create a coupled harmonic oscillator model so that we can find our exceptional points. We're going to start with microwave cavities that we built in-house, and these have tunable resonant frequency and tunable dissipation rates. Then we're going to combine that with an oscillator that we realize from yttrium iron garnet, because this is going to be our sensing parameter since it changes with magnetic field. We used wire bond loops to create an oscillator from this YIG, and the whole reason why this is important is because the frequency of the YIG is now magnetic field tunable. We couple this to a current-controlled electromagnet, and by changing the current, we can change the magnetic field, which changes the resonant frequency of the YIG. So, we have our two modes, we're going to couple them together, and the way that we do this is by spatially separating these two oscillators and connecting them with wires. And the reason why this is cool is because we can put unidirectional amplifiers on each leg of that coupling path, and with the variable gain of the amplifiers, we can do this. We can see that our two modes are hybridized together, but we can increase the gain between these two modes to give ourselves tunable coupling. My colleague Juan just published a paper 18 hours ago now that showed this in two microwave cavities, but we're doing the same thing between a Magnon and a photon mode. So this is where things get really interesting. We're going to put a phase shifter on one of these legs, and this will allow us to switch between different modes of coupling phase. So we can switch between level attraction and level repulsion at will, and we can even go anywhere in between 0 to 2 pi, but we find that 0 and pi, or reciprocal and anti-reciprocal hopping, are the two most interesting regimes. And this is going to allow us to see the EPs that we're looking for. And once again, this is based on work that we just published yesterday for two microwave oscillators coupled together. Finally, we take these two modes and we put self-feedback loops on them. That allows us to control the constructive interference or deconstructive interference between them, which allows us to change the dissipation rates of both of the modes. So you can see that we can get constructive interference, which gives us super high line width on each of the modes, or deconstructive interference. So, with all this control, this allows us to universally realize all the parameters of a two-dimensional coupled oscillator system. We have the frequencies of both modes, we have the dissipation rates of both modes, we have the coupling strength, and we have the coupling phase. So now that we've got the platform out of the way, let's use it to build some exceptional points. First, we have to find them. So to do this, we're going to dig into some math, we're going to do some spectral analysis, and we're going to find where these EPs are. We start with the full dynamical matrix for the coupled system. This includes all of our parameters, including these self-feedback loops and the drive detuning. But we're going to simplify it by replacing the individual frequencies with a detuning parameter instead, and replacing the dissipation rates with a detuning of dissipation instead as well. This allows us to write an effective Hamiltonian, which is easier to work with and has cleaner eigenvalues. But what's interesting is we're not actually caring about the eigenvalues themselves, we're caring about this term that we call the eigenvalue splitting, which is the difference between the two eigenvalues. Then we combine this with a method called Peterman factor. The Peterman factor is a way to quantify the non-orthogonality of eigenstates. We're looking for where the Peterman factor diverges, and that means that these eigenstates are on top of each other, signifying an exceptional point. Solving this, we don't find one exceptional point or two. Instead, we find an infinite family characterized by what we call an exceptional surface, and that allows us to realize an infinite family of exceptional points using our tunable parameters. For this talk, we're just going to talk about one of these exceptional points, which we call the anti-reciprocal exceptional point. So what does this look like? Well, by looking at the imaginary eigenvalue locations, we can see this characteristic square root splitting that we've all come to associate with exceptional points. Furthermore, I'm going to actually plot the transmission experiment of our simulated system on top of this. What I mean is that the imaginary eigenvalues don't tell you exactly where the frequency peaks will appear for your experiment. Instead, we're going to simulate those directly. And what we find here is that we get the same square root splitting in our transmission experiment. It just happens a little bit after the exceptional point. You can think of the exceptional point as setting the bounds for the frequencies that you'll actually see in experiment, but they're not exactly equal. Next, we'll look at the real eigenvalues because this will tell us something about where the instability bifurcation occurs, where our system starts to go unstable. And what I really want to highlight here is that the exceptional point itself is purely a spectral bifurcation. It doesn't tell you everything about what the experiment is going to do and where those bifurcations occur. Instead, the bifurcations for the frequency splitting and the instability transition are symmetrically separated from the exceptional point because there's loss present in the system. So this is our experimental data. We did this in our tunable platform. We set it up to do the anti-reciprocal exceptional point, and this is what we got. So let's run through this little by little. The first thing I want to draw your attention to are these shaded regions. What we did here is we predicted all the possible peak locations that could show up when you factor in all of the experimental uncertainty in our system. So in that beginning introduction slide, I changed one parameter by 3%. This is accounting for all the experimental uncertainty in our system, and you can see that the peaks will possibly show up in an entire range. But what we might notice here is that the data deviate from the model near the exceptional point. And fundamentally what I want to draw your attention to is exactly around the exceptional point, these two possible ranges of peak locations start to overlap on each other. This is the perfect description of what this peak indistinguishability is. Even when you just theoretically simulate these locations of the peaks, if you include all of the experimental uncertainties, they are overlapping with each other and you cannot differentiate from them. So we agree with the literature that because of this peak indistinguishability problem, where you would normally have the most sensitive location for the exceptional point, that is diminished due to this indistinguishability. However, what we noticed about the anti-reciprocal exceptional point is that it is also an instability transition. So as you cross it with detuning, you go unstable. Maybe we can use this for sensing. So the premise, what we're going to do instead is, instead of tracking the locations of these peaks as they split apart because they're undifferentiable from each other, we're going to pick a single frequency, we're going to drive and read out at that frequency, and we're going to measure the amplitude that we measure from that system. And as the peaks split, it makes sense that as they move further apart, if you measure in between them, that will move down. But what's interesting is that past the exceptional point, as the system starts to go unstable, this power versus perturbation strength, which in our case will be magnetic field, grows exponentially in log dB scales. So what does this look like in experiment? So we put a anti-reciprocal exceptional point sensor up against a sensor just built from the yttrium iron garnet sphere, and we find that past this instability transition, the response of our anti-reciprocal exceptional point sensor is much higher than the response of the YIG by itself. And this is mainly due to this instability transition, which causes the amplitude to grow wildly. So we've got a paper cooking, and it's about to be done on this setup and our results. So one thing that I just wanted to highlight here, if you're interested in our paper when it comes out, is we did all this same analysis for a second type of EP which we call the reciprocal EP. And what we find is that the reciprocal EP has the same peak indistinguishability problem. It has the same reason why you couldn't use it for frequency splitting based readout. But it doesn't have the instability transition, and because of that, we can't even use it for homodyne amplitude sensing. It doesn't perform very well. So it's something about this instability and nonlinear transition that is so important. And if you stick around for part 2, my advisor, Professor Fitzpatrick, is going to talk more about nonlinear sensing and how we can use that as a resource to improve our sensors. So for a summary, we built a platform where you can tune all the parameters of a coupled oscillator system to find exceptional points. We find an entire exceptional surface. We agree with the literature that frequency splitting based sensors are challenging, and we use this homodyne amplitude and instability mix to have a promising way forward. So thank you, and stick around for part 2.